Oklahoma, Texas, New Mexico, and Louisiana. The organizations that form up that consortium are OU, God's Country, OSU, LSU, Texas Tech. Then we have one federal laboratory, the NOAA Geophysical Fluid Dynamics Laboratory. I'll tell you a little bit more about them in a few minutes. And then finally, we have two sovereign tribal nations, the Choctaw Nation of Oklahoma and the Chickasaw Nation. They are full consortium members. They sit at the table, they make decisions just like anybody else in the consortium. Okay, so we're co-governed by this consortium as well as the federal government. Makes you get along really well when you, when you share governance like that. You all have to communicate a lot. So what do? The main thing that I spend my time doing is funding research. And we want that research to be research that benefits folks like you that are actually managing cultural and natural resources on the land. Okay? So we have a group of stakeholders. We call it our Stakeholder Advisory Committee. They help us decide which research we should fund each year. These are folks from federal and state agencies, as well as some tribal organizations that help us make these decisions. We also do outreach and training, and then we also do some technical assistance. So we help managers and planners understand climate science, how it works, and how to integrate it into their planning and their models. So one of the questions that we try to help people answer, is why does climate change matter to them? Well, the reason it matters is because in the near future, we're going to see increases in drought frequency. We're going to see changes in temperatures, extreme events such as flooding, and we're also going to see changes in the growing season length. All of those things affect those of you who do burning on a regular basis, I'm certain. Okay, let me back up a little bit, and I'm going to talk about how we do our climate projections. So I work with some really smart folks. These are basically applied physicists, okay? Those of you who remember physics, I think I had it in high school. Those of you who remember physics know that it's mostly math. They take the physics of the climate, put it into mathematical models, and to do that, they have to divide up the globe into these little cells. You can see the cells there in the little blue globe in the bottom of that picture. The idea here is each one of those cells has a unique set of climate variables, and we do what we call time step it. The model moves it from one day to the next day, assuming that one day is the time step. Sometimes they move it, 1 month at a time, 1 year at a time, depending on what your time step is. But anyways, the whole globe, the entire globe, is divided up into thousands of these little cells to do these calculations. They project this forward. Typically, we do it until the middle of the century, around 2050, and then the end of the century, 2100. This takes enormous computing power. Literally, these models will run on a supercomputer for a month. Okay? That is outrageous to me. That we are talking petabytes of information. A figure that me in my training as a wildlife ecologist, I had no idea what a petabyte was until I started working for these folks. So just storing their data, not just generating, but just storing their data and transferring it from one scientific center to another is a huge part of what they do. Okay. So now on to a little bit about what we can expect for our region. Okay. So I'm going to show you a group of slides. On most of these slides, you will see two pictures like this. And you notice down in the bottom of the caption on each of these, it says RCP. The ones on the right have a lower RCP number. Well, I guess that's your left. The ones on your left have a lower RCP number, and the ones on the right have a higher number. Basically, think of these as best case scenario on your left, worst case scenario on your right. The climate scientists cannot tell you exactly what's going to happen with the climate because they can't tell you exactly how much emissions, how much greenhouse gas is going to be emitted by society. If our society as a whole, as I like to put it, gets religion and we decide that we're going to cut off all our carbon emissions tomorrow, that's basically the best case scenario. If we continue on a path that is business as usual, the way we've been doing things up until now, that's the worst case scenario. So as you can see from this graph, we expect, or these two maps, we expect considerable, for our region, considerable temperature increase in the near future. This is, I'm sorry, I can't see it. Okay. We can also divide that up into seasons, okay? So you'll notice in this graphic, now this is just the worst case scenario that I've thrown up here. In this graphic, the summer season, which is bottom left-hand side, shows you it's generally going to be hotter in the summer. We're going to see more temperature increase in the summer than we will in the winter in our region. Okay, again, back to the worst case, or best case, worst case here. I'm sorry, I can't quite see it. Oh, days with temperature above 100 degrees, is that right, John Ware? Thank you. John, you're gonna have to interpret for me. Okay. Days with temperature above 100 degrees. Average annual number of very hot days. So we're considering very hot days to be greater than 100. I don't know about you, but I don't think I want to live in South Texas in the not too distant future. Okay, if this comes true, we are talking as much as 30 to 40 days, additional days above 100 down there. That corresponds to my definition of miserable. Okay, we can also take these temperature projections and split them out by a point, a city. So in this case, we're talking about Lubbock, Texas, for example. Let's see if my pointer will even work. Hot dog. So this is, again, best case here. This is kind of a medium case, and this is worst case. In Lubbock, you can see that we're expecting a pretty good 10 days, pretty good increase in the number of days above 100 degrees, 10. But if we go, that's with the best case scenario. If the worst case scenario happens, again, 30, 40 days of temperatures above 100. Now again, this is on average. This is for the end of the century. Okay, we're not predicting. You'll notice that I refer to these as climate projections, not climate predictions. Your weatherman gives you predictions for what a particular day will be. This is a projection of the averages towards the end of the century. Growing season length. So we have these projections on a daily basis we do it when we're looking at the end of the century, we do it for 30 years, so we can figure out what is the average growing season length, the time between freezes, okay? We're projecting a considerable increase, especially on the worst case scenario in the northern latitudes of our region. The southern latitudes, we don't expect it to change much. Any guesses why that is? That's right. He said because it's almost 365 days a year growing season anyways. Exactly right. You can't get any better than that, can you? Okay, so we can also give you some precipitation numbers, okay? Now, the climate scientists are a little less certain of the precipitation numbers than they are of the temperature numbers. The reason is temperature is pretty straightforward. It's just basic energy in, it heats up the atmosphere, you got higher temperatures. But with rainfall, you're talking, you have to understand that there's a certain amount of lift in the, you gotta have the moisture there, but then you have to have lift to get the clouds up high. The climate sciences like Monica can tell us all about that, but I'm not a climate scientist. Suffice it to say that the rainfall is just a little more complex to predict, and so our certainty about that is a little bit lower. So just a caveat about that. And you'll notice in these, again, we have worst case on the left, best case on the left, worst case on the right, and these are changes again this is the mid-century. In the worst case scenario, we can see considerable drying in West Texas, eastern New Mexico, and western Oklahoma. In the best case scenario, we see little change, maybe a little bit wetter in Oklahoma and South Texas, a little drier in southeast New Mexico. So again, we can break that up seasonally. You'll notice again, hot, dry summers like we talked about before, more high temperatures, less precip in this region again. Not a good outlook when that region is already so dry. Projected change for the mid-century, average annual number of days with precipitation. So one of the interesting things about these models is most of the models that they're running show us we'll get, probably about the same amount of rain, maybe a little bit less, maybe a little bit more. Again, there's uncertainty there. But the rain will be concentrated in fewer storms. Now this is good, perhaps, if you like to burn. Have more days without precip, maybe. But it's not so good if you like infrastructure. If you like roads, bridges, dams. We're going to see more erosion. We're going to see more heavy rain events, probably more flooding. Okay, so the models that we run give us two things basically. They give us precip and temperatures, high and low temperatures. But from those things, we can spin out all these variables, plus more. So I'm going to put my contact information up here soon. If you're interested in any of this information, please don't hesitate to contact us. We are there to help you all out. This is an example of the kinds of data that we can provide to you, kinds of information we can help you out. If just by chance there's any modelers here in the audience, if you would like to integrate climate change data into your models, let us know. We'll be happy to help you with that. We'll be happy to provide it to you. This is just a smattering of what we can do. You tell us what you want and we'll see what we can do to get there. Just a word of caution, we can tell you about the climate, what it's going to be like mid-century, what it's probably going to be like end of century. We can't tell you how that's going to affect whatever resource you manage. So let's say you manage a particular grassland that's partially getting overrun by cheatgrass. What's the impact of higher temperatures and probably a drier environment on cheatgrass? I don't know. I'm not a cheatgrass expert. I hope, if you're managing that, I hope you are. So you can try to figure out whether you're going to get more or less cheatgrass in the future. So we can help you understand the climate. We will work with you in your planning and your modeling to help understand what the impact will be on your particular resource.